Now let's give some details about how the algorithm, the methodology works. First, we can remember that we have a function r of theta, theta the vector of all the parameters that are involved in the neural network. We have a sum I equals 1 up to capital N of yi, the output, minus h theta of xi up to the square. This is a sum of residuals that you always have in multiple regression. Here we simply have a vector theta which can be very large due to this. To solve this, since we have a very complicated function with an activation function which may be a g function, it's important to find algorithms that work efficiently. And it's not possible to solve this problem analytically, as it is the case when we work with linear regression. Thus we have an iterative algorithm. This is solved, for example, by a well-known technique which is named the gradient descent. This is a technique which sees this function as a function in the space, and we try to find the direction where the minimum, where a local minimum that we hope to be the global minimum, we hope that we try to find the best direction such that we go progressively to the minimum of this function. And the minimum of this function defines the theta. This is named the gradient descent. That means that step after step we have to update what is inside the vector theta. We have initial values of theta and we use this gradient descent until we find the supposed minimum of this function. This is an iterative technique. That means a technique which needs to take initial values in this vector theta. Now let's say that we have starting values for theta and we begin the algorithm. We try to find the minimum of this function r of theta. And it is calculated with a technique which is known as a gradient descent. It computes the different derivatives of these quantities with respect to theta and with respect to the components of theta, and at each iteration it tries to find, with these derivatives, it finds the best direction such that the algorithm goes closer and closer to the minimum of the function. Next we have some equations that when you combine themselves together, it's also possible to find, to update, let's say, the different components of the vector theta in a very efficient way. That's also the reason why we named this kind of algorithm backpropagation algorithms. Now, it's possible that now at the end we should find a value of theta which is the minimum of this function. But it's well known that a gradient descent has some problems. When you implement a gradient descent, this algorithm depends on what we name the learning rate. The learning rate can be seen as the speed we use to find the best direction, to go in the direction in order to reach the minimum. But these techniques have some problems. In particular, it's possible that at the end it finds a local minimum. It should find the global minimum of this function r of theta, but sometimes it finds a local minimum, and in this case it's not the good solution. Therefore, that's a flow of this kind of methods, and that leads to a problem for neural networks.